hello to everyone. My name is Klaus Blaum from the Max Planck Institute for Nuclear Physics in Heidelberg. I'm the chair of today's session. So let me briefly introduce our speaker. Today it's Professor Dr. Klaus Kirch. He is the head of the Laboratory for Particle Physics at the Paul Scherrer Institute in Willingen in Switzerland. And he is also full professor at the ETH in Zurich. Klaus is a true expert in neutron and muon physics. And we are very happy of having him today here as our webinar speaker on ultracold neutrons and the neutron electric dipole moment. As usual, in case of questions, please type them into the chat or into the question and answer window. We will address them at the end. And Klaus also offered that if there's an urgent question, you might raise your hand and we will then drop them in right away. So have fun, and Klaus, the floor is yours.
Okay, thank you very much, Klaus. So it's the other Klaus speaking here. Good afternoon from my side. A great thanks to the organizers. I think that's a wonderful idea to have these web seminars. I enjoyed the first two, and let's see, I hope I can make it a little bit enjoyable for you as well today. The pictures you see on this slide sort of give a trace to what the talk will be about. So we have to do with questions that concern cosmology, and there I connect to what Dima Budka was talking about last week. We do our research at an accelerator facility, so you see a picture of our machine down here. We produce ultracold neutrons with some instrumentation that you will see, and then we measure the neutron electric dipole moment. A picture of the apparatus that gave the present best result is shown here, and the next one will hopefully come from this device down right there. I decided to sort of make 3 chapters for this talk today. There will be a relatively long first chapter. There will be a shorter one as the second, and the third one will be as short as time allows. Still, what's left over, we'll see. Now let me start with neutrons and ultracold neutrons, because I think we have to understand where they come from and what we do with them. All of you obviously know that the neutron is a massive composite particle. It's electrically neutral, as good as we know, some 10 to the minus 21 electron charges, so is the limit. It's unstable, so the weak interaction decay you see here, where it decays to a proton, electron, and electron antineutrino. It has a spin 1/2, it can be polarized. The spin 1/2 comes with a magnetic moment. What we are after is the question whether it also has a permanent electric dipole moment. A feature that will come back is something may be obvious to you, but it's a peculiarity of the neutron. It takes part in all the known interactions. So you see the weak decay. It's obviously a strongly bound system. It also binds in nuclei with a strong interaction. It has a magnetic moment, so it takes part in the electromagnetic interaction via that at least. And it's affected by gravity if it's slow enough, and we'll use that as well. If you look at the nuclear chart, you see the neutron down here sort of as the lightest unstable nucleus, although it's never a nucleus of an atom. It forms with just something surrounding it. But nevertheless, it's a constituent of all the other nuclei that we have. And they are the neutron traps that we must use. So if you want to do an experiment with neutrons in your lab, you will have to produce them by freeing them from the neutron traps that the nuclei provide. There may be other ways how you in principle could produce pairs of neutrons, antineutrons, or things like that, but that's as inefficient as can be. You see the half-life given here, 10 minutes. So the lifetime is around 15 minutes of the neutron. So the ones that were produced in the early universe, they are all gone or eaten up in nuclei. And this is shown here, a picture that perhaps you've seen many times already. So this is showing the time after the Big Bang, or the temperature, the cooling of our universe. And in the beginning, when we formed already protons and neutrons, but they were in thermal equilibrium, at some point decoupled. And then it's the neutron lifetime that determines how many neutrons are still left over when you start to form in Big Bang nucleosynthesis the stable nuclei. So helium-4, for instance, the abundance of helium-4 in our universe, the primordial abundance, is sort of given by a parameter that's the neutron lifetime, among others. And then you have the deuterons, the helium-3, and so on, the less abundant primordial nuclei. So neutrons are interesting for that, for instance, to measure the lifetime, to know about Big Bang nucleosynthesis and other things as well. Now, if you think of producing them in your lab, you look at what you have available in nuclei. You find this graph, which is the average binding energy per nucleon as a function of the nucleon number. And you know that you can gain energy by fusing light elements. You can gain energy by fission of heavy elements. But now you want to get free neutrons just in your lab. And then in your lab, maybe you have DD or DT generators that produce neutrons. Maybe you have a few 10 MeV accelerators for protons. You can bombard light elements like beryllium or boron, get neutrons out of those reactions. But what I've also put in parentheses here is what you have to put into your target as heat to produce a single neutron. So 10 GeV or 1 GeV. So you see, instead of using a DT generator, maybe if you can use a beryllium target bombarded with protons, that's a factor 10 already more efficient. So it means for many, many neutrons, you have to do much less target cooling. And this continues over here. If you look here, this is what we call spallation. This is what we use. So that's another order of magnitude more efficient. And fission is as well, right? I mean, but has some other problems that you have to deal with the fissile material. So we'll be concentrating on spallation, where you see you can release neutrons from nuclei by putting a few 10 to 100 MeV or so per neutron into the system. This is how it works. The fission you know well, I guess. So when you, for instance, in uranium-235, eat a slow neutron, have the fission, you release a number of neutrons, part of which you use to sustain the chain reaction, and the others you can take out and use in your research. In the spallation, you typically have a proton accelerator, some few hundred mega electron volts to a few GeV you use. You bombard a heavy nucleus, say a lead nucleus in our case. You deposit a lot of energy into this nucleus that has to equilibrate somehow, will be highly excited, and will eventually evaporate nucleons. So, and you get, for our energies, for instance, of 600 MeV, on average, some 8 useful neutrons out of 1 proton that you put into the system. If you look at the energy distribution of the fission or spallation neutrons, what you find is that they both have a maximum or mean energy around 2 MeV, but then they have a different behavior on the high energy side, where the fission in a nuclear reactor, you don't have many fast neutrons, whereas you have many of those from a spallation source, actually up to the energy of the protons that hit the nuclei, right? You can have among the equal mass proton and neutron, you can essentially transfer all the energy of the proton to a neutron and have a very fast one. So this is shown here for 1 GeV proton beam. Then on the low energy side, both of them essentially fall. And what we are now interested in our research is the very slow neutrons, the very low energy ones. And obviously we have to somehow get those from the peak over here, as many of them as we can. Now, if you do that, you know well from reactor physics, I guess, that you have to moderate such MeV neutrons to thermal energies. What is given in this small table here is for a number of elements with their nuclear masses, just the number of collisions on average that you need to go from 2 MeV, this mean energy after the fission or spallation, to thermal energies. And you see that if you have hydrogen, say a light water moderator, you need 18 or so. And if you have heavy water, for instance, you need something like 25 collisions on deuterons to moderate that. And you see as it's getting more and more inefficient if you use heavier stuff. That's clear just from the kinematics, where you bounce off equal mass or just twice the mass of the neutron, or much heavier systems, right? So we'll use deuterated systems all the time in our research here. The big advantage over protons is that the absorption cross sections for neutrons is on deuterons a factor of 600 or so smaller than on protons. So the neutrons can live much longer in a moderation system that's made of deuterons and some other materials. This is just for you to look up how that goes with the moderation. If then you have thermal neutrons, you can really start to think of them as being a gas. So please, if you think of a large water tank where you moderate the neutrons in. The neutrons come into thermal equilibrium with this water, say, and they will form a gas with a kinetic energy here on average of 25 millielectron volts. And then in the 1930s and 40s, when Fermi and collaborators did many of the basic experiments with neutrons, they found already that thermal neutrons, and then more so cold neutrons, can be totally reflected from material surfaces when they come under grazing angles of incidence. And as the neutron energy goes down, this angle can get larger and larger. So it's like total reflection of light from a surface. You have total reflection of neutron waves from a surface. Now, if you cool them, this total reflection angle is getting larger and larger. So it's obvious that you find at some point that you can reflect under 90 degrees. So you get total reflection under all angles of incidence. And this is exactly a definition of ultracold neutrons that we use. You will see it's not a good definition because it depends on the material that will have different potentials, optical potentials or Fermi potentials, we say, but a typical number here would be, say, 200 nanoelectron volts for that. So ultracold neutrons with kinetic energies below that material potential of the surface here will be totally reflected. So this is a cut through the ILL, high flux research reactor in Grenoble. The fuel element is sitting down here. That's a uranium enriched 235 uranium fuel. Here's a large heavy water moderator. So you produce thermal neutrons in here. And as I was saying, they are like a gas. So you have a Maxwell-Boltzmann velocity distribution to very good approximation, right? I mean, there are tiny deviations from it. Don't nail me on it, but a very good description is a Maxwell-Boltzmann here at 300 Kelvin for the water. Now, if you're interested in the very low energy ones here in the tail, I apologize for something being cut here. I thought it's only cutting the logo, but it's not. But it's nothing very serious. You see, this is a function of velocity shown here. We could show it also as a function of energy. If you want to see the very low energy tail here, this is only about 10 to the minus 13 of the flux that you have in the total here. So if you cool the neutron spectrum, say to 30 Kelvin, and this is done here. Here's a liquid deuterium cold source in this reactor. So the thermal neutrons come into that, they again make a few collisions, and then they are cold as the liquid deuterium almost, and you get this 30K Maxwell-Boltzmann distribution, and you enhance in the tail by a factor of 70 already a number of slow neutrons, ultracold neutrons that you can have there. And then at the ILL, that was and still is an operational facility that takes then those very cold neutrons from the tail here out vertically into a mechanical deceleration device to then distribute ultracold neutrons to experiments. This is all mechanical. There's some gravity involved, but then Liouville's theorem of phase space conservation will tell you the density of the ultracold neutrons that you have here cannot be larger up here in that respect. So this is a thermal source in equilibrium with a moderator, and then you play some tricks to get the interesting neutrons out. Now, those ultracold neutrons, I told you already, when they come from vacuum, they can be reflected by material walls. This is actually an effect of the strong interaction, the so-called Fermi potential or Fermi pseudo potential you find, or some people call it the material optical potential. That's all the same. So it's typically on this order here, right? So kinetic energy, say below 200 nanoelectron volts, we want to reflect, we have a material wall with that potential. Now, I told you already they are spin 1/2 particles. They have a magnetic moment, so they will have a mu dot B magnetic interaction, and that amounts to 60 nanoelectron volts per Tesla. Okay, so means decent laboratory magnetic fields that we can have nowadays in our labs easily provide potential barriers on the order of the kinetic energies of those ultracold neutrons. So you can also trap them magnetically. You see here that obviously because it's proportional to mu, there will be two spin polarizations. So it can be either a potential wall or a well. And so for some it will be repulsive, for others attractive. And then last but not least, also the gravitational interaction. If you take the gravitational potential energy, just put in the neutron mass, This amounts to 100 nanoelectron volts per meter. So our 200 nanoelectron volt neutrons will just climb 2 meters in the Earth gravitational field before they fall down, right? So all in all, they form a gas that you can contain. In many respects, it's an ideal gas. Only it's non-interacting. Unfortunately, our densities of ultracold neutrons are always so small that they never interact with each other. And they are not in thermal equilibrium with their surrounding. I can build a wall of a room temperature, stainless steel, for instance, if you wish, and I can store them in that, and they will have, if you calculate from their kinetic energy, still millikelvin temperatures. It's not the right concept, temperature here, but this is just calculated from the kinetic energy. Important to realize at this point is when you have a reflection like that, say a neutron coming to a room temperature wall, the incoming neutron kinetic energy and the outgoing neutron kinetic energy is the same, right? I mean, so it doesn't pick up energy from the wall. Well, there are effects where it can do that, but in general it doesn't. So this temperature of the UCN gas is maintained. Calculate the velocities of those 100 nanoelectron volt or so ultracold neutrons. They are a few meters per second. Their wavelength, if you calculate those, are tens of nanometers, maybe 100 nanometer, 1000 angstrom. So getting into somewhere far ultraviolet light region. So many of the optical properties for ultracold neutrons are things that you can also see with your eye. So far, I told you about thermal moderation. Now I want to introduce a concept that's called superthermal. And what you should look at is this picture down here. I take a cold neutron and put that into some material, say a solid, a crystal, and so it can scatter off the crystal lattice. And in the scatter, it can do something that neutron scattering people would call inelastic. It will produce a phonon in the crystal and lose kinetic energy by that. So assume it loses so much kinetic energy that it's an ultracold neutron afterwards. It generated a phonon in this crystal, but now I cool this crystal. So cooling means nothing but you take out all the phonons, right? So if you produce a phonon, let's take that out by our cooling machine. So the reverse process where a phonon hits an ultracold neutron is strongly suppressed. You probably know the concept of detailed balance. So you can downscatter these cold neutrons to ultracold neutrons, but by an exponential term, you suppress the upscattering. So in this way, I can continue producing ultracold neutrons here without losing them, and they will not be in thermal equilibrium with this material. If I do that, the density of ultracold neutrons that I can generate here will be proportional to the incoming neutron flux, right? Twice the number of them will give twice the number of UCN. There is some macroscopic cross-section for the scattering process to happen that transforms this energy to that energy. And there will be a limited lifetime of the ultracold neutrons in this box here that I sketched, okay? So the product here will give you the density that you can achieve in equilibrium when the production and the death of the UCNs just equilibrates. Now, typical materials for this process are superfluid helium, which has a smaller production, but a very long lifetime possible for neutrons in this soup, and then solid deuterium, which has a larger production cross-section, but a shorter lifetime. For both these, the production has obviously been measured, and both these graphs show the same. This is a momentum axis of the neutron. This is a kinetic energy axis of the neutron, so essentially the same. And on the vertical axis, you get for these measured points, counts of ultracold neutrons that were produced. And here, this is also counts of ultracold neutrons or a cross-section here. And this can also be translated into a cross-section. Let's start from the helium. That's somewhat simpler. So you have a momentum here. You have an energy here. So the free neutron will be just a parabola, right? I mean, the energy, the kinetic energy is just 1/2 mv squared. So it's just this parabola here. And then the dispersion curve in superfluid helium, you have the phonon branch here, you have the protons, is this curve. So if you want to excite some phonon in the superfluid helium, you have to bring a certain minimal energy, and that's here. right? So if the neutrons have this energy, they can produce a phonon in the superfluid. The neutron will lose its kinetic energy, will sit down here at 0, and the phonon will be pumped away by cooling. So this way we get this peak here, and then there are some multi-phonon processes which are over here. For the solid deuterium crystal lattice, there are much more, it's a much wider phonon spectrum, so you can produce ultra-cold neutrons over a larger range. And this is just a fit with a simple Dipole model of a solid, and then you have 2 and 3 phonon production also possible. But just to tell you, you can produce it, and it works this way. And those ultra-cold neutrons are not in thermal equilibrium with this material you produce them in. Now, if you want to have a very crude estimate, I give you this table where there are production cross-sections and lifetimes. The take-home message from this is deuterium produces about a factor of 10 stronger than superfluid helium, but the lifetimes in superfluid helium can be 2, even 3 orders of magnitude longer than in the solid deuterium. So in effect, you can in principle get 2 orders of magnitude higher UCN densities in the superfluid helium than you can in the deuterium, given you would have the same cold neutron flux. And here comes the problem. The solid deuterium you can use at, say, 5 Kelvin. The superfluid helium has to be at 0.5 Kelvin. And now you have to maintain a cryogenic system at this temperature in as high a cold neutron flux as possible, meaning in a reactor close to a fuel element, meaning in a spallation source close to a spallation target. And therefore today, deuterium sources have been put close to such targets, superfluid helium sources not yet. So while this term gets larger for the helium, this term here is still smaller. But people are working on trying to get also superfluid helium closer to the very high intensity regions. So this is just something for you to look up later. We are at PSI, somewhere here, we have a running ultra-cold neutron source. We think it's the best in the world, but many people will do that. Other people have sources or try to build them, and you can look up what they are doing. The operational ones have deuterium in one or the other way. If it's a high flux thing, if it's on extracted neutron beam, there are also superfluid helium sources around. Let me come back for a moment to this ultra-cold neutron potential of a wall material. And here you see a table where in this column, we have material potentials, right? And because this seminar is something where I also wanted to teach you something, I take this opportunity to show you something which I've always found amazing. So let's see whether you can appreciate what I mean. For instance, take nickel, this is 250 nanoelectron volts, or carbon, depending on which form you have, a dense graphite, 180, or similar to iron is stainless steel, 210. So we have regular materials we can use to trap ultra-cold neutrons. And then you could continue the list for very many materials, and you would find that most of them are positive in their potential, repulsive potentials, and only very few you find which are attractive. And now why is that? And this is something that's beautiful but simple nuclear physics. It's because the neutrons are so slow, it's a pure S-wave scattering, and you can assume that the nuclear potential would just be a square well. If you want, you can use some fancier potentials. It doesn't matter, it doesn't change anything. I can just parameterize it, say, by a radius, here just by the size of this box potential that I use. And then I have coming from the outside a very long wavelength neutron. And then I know this is a very deep potential well. So inside the wave function will be oscillating very rapidly, right? And then you have to have a connection here of the wave function must be continuous and the derivative must be. And then you know in S-wave scattering, the whole scattering process is described by just one scattering length. And this can be positive if the axis is intersected here, or if you here do the asymptote and it intersects at the negative values, it's an attractive scattering length. Now, there are different conventions. In my convention, repulsive is positive scattering length, and attractive is negative scattering length. Now, whether it comes out positive or negative only depends how you continue this wave function here. And this will strongly depend on the size of the nuclear well potential here. So on the nuclear radius. And you know the wavelength here of the neutrons was on the order 10 nanometers, whereas the nuclear potential is in size only femtometers. And now if you imagine that you have different isotopes, you change a little bit, you add just one nucleon or so, and then the radius will change a little bit. Yeah, sometimes more, but a small amount only, but something that we cannot predict. It's really more or less a random process. And thereby I can randomly see how would it develop if I have to connect those two waves here. And what I find, if I do that, I find mostly positive scattering length. This is for all nuclei where we have scattering length measured, the scattering length. Here is 0, right? So above this 0, everything is positive, and you see that most nuclei actually fall on the positive side here. Some do on the negative. You see the scatter, which is large, which means this is really something we cannot easily predict, but you can fit the mean values here and you get this red line. And if you project onto the red line, you find this distribution. And this is now just a fit to one parameter, which is this R. I take it as the R, say, would be for the radius of the nuclear potential seen by the neutron. It's not a real physical quantity, but you see the order of magnitude comes very nicely. And then it's just multiplied by 8 to the power 1/3. So a nuclear radius type thing, right? As the volume grows, like the nuclear number, the radius will grow like 1/3 power of the nuclear number, and you get a very nice fit to that. And that's a Gaussian, and you see that all the nuclear, all the data we have is nothing but a random distribution in nuclear size and an S-wave approximation, and it's here. So that's sort of fun, and there's a very pedagogic paper if you want to read that, that can help you. People have used that, Neshvishevsky and Pignol colleagues, to see whether there's some exotic interactions that you wouldn't expect here. And they have collected much more data that's in there. But I think that's very beautiful. Okay, if you want to know more about ultracool neutrons, there are textbooks, actually 2 of them. I show you one here. And this is just to tell you, if I know the scattering length of a nucleus, and I put them together in a certain density in a material, I can calculate for you the reflection potential, the Fermi potential of that material. And it's as easy as that. Now, we do our research at PSI here. If you don't know where that is, it's in the northern part of Switzerland, where you probably know where Geneva and CERN are. We are between Zurich and Basel. If you haven't been there, come by and visit us. After the Corona crisis, I can do tours again. It looks like that. If you look towards south, you see the Alps over there. This is the River Aare. And then on both sides, on the east side and the west side of the river, there's the institute. And the particle physics at PSI is all in this experimental hall over here. Inside that is this ring cyclotron that you've seen on the first picture already. It accelerates protons to close to 600 mega electron volt kinetic energy, which is nowadays a very low energy. But it's unique in the way that it has a very high current. It's a 2.4 milliamps in the current. So if you multiply the energy by the current, you get the power, which is 1.4 megawatt in the beam, right? So this is the highest power continuous beam to targets that you find in the world. And we use that to produce pions, muons, and neutrons. It sits in this corner of an experimental hall that you've seen on the picture before, and usually the beam will go here, produce pions here, pions there, they decay to muons, and then it's dumped in a neutron, spallation neutron source, mostly for neutron scattering material science. We can take the full beam also to a dedicated spallation target over here, and that you see in more detail here again. Here's a fast kicker magnet, allows to switch the full beam, the 2.4 milliamps, to this target station here. You see a little bit bigger view here. I show you on the next transparency another one. And then we produce ultracold neutrons in this device and distribute that to 2 areas and 3 beam lines. And one of them feeds the neutron electric dipole moment experiment. This is a cut through the source. You see it's a pretty tall tank, some 7 or 8 meters high. Down here, the proton beam, say for typically up to 8 seconds, we take the full beam. So that's, we call that a macro pulse. Several seconds long pulse of protons hitting a spallation target. Essentially, it's solid lead, but it's a talk by itself how you make a target. But You produce then from the lead nuclei, as I was telling you, the mega electron volt neutrons. They will be moderated in a heavy water tank here, some 3.5 cube meters of heavy water. And then part of them comes into this heart here, which is a cold source again, but now we have solid deuterium in here, about 30 liters of solid deuterium at 5 Kelvin. So some neutrons that become cold in here will downscatter to form ultra-cold neutrons. And now we do something that enlarges the lifetime of the neutrons in the system. They don't have to only survive in the solid deuterium, they can get out into vacuum and must survive in this system here. And the lifetime in this system here is a few seconds. So we can, for a few seconds, produce neutrons until we reach equilibrium between production and loss. And then we can close these valves here and trap the neutrons by the material optical potential of this trap. Actually, this one is diamond-like carbon coated because that's better than just stainless steel or something, but this is a detail. Now, think of the ultracold neutrons being a gas. They fill this volume, they bounce around. What's affected by gravity, so they will not reach the cryopump on top here, but be on parabolas, ballistic curves here. Part of them will exit through this UCN guides, the neutron guides, and that's like plumbing. So you have a tube evacuated, but your neutron will find its way to the experiment. Here you see that again, a long guide bringing something to an experiment. At the end of the guide, for instance, there can be the guide going through a 5 Tesla superconducting magnet. And then you know, oh, that's for one spin direction, a huge potential barrier. So they will remain in the source, but the other spin component will come out. So what you get on the other side is fully polarized ultracold neutrons. And here are some impressions from installation of the beast. Here's the storage tank, for instance, with this prolongation down here that you see on the photograph here. The storage tank, actually, we cool that to 80 Kelvin. You could use room temperature storage. It's somewhat better if you cool it, but that's, again, some detail. And here you see the insert with the deuterium moderator vessel, the yellow one over here, and these two flaps. You see them up here, besides Bernard, who's holding the piece, because that's a huge pendulum that is now inserted from the top into this tank. Make sure that it doesn't touch, because there's only a few millimeters of play that you have. The source is in operation since, well, let's say since 2011. We had first pulses in 2010, but then we didn't get much out. We improved that. And over the years, every year or so, we improve a bit. I stopped this graph in 2013, but every year it's some 20% or so better since then. And the reason it's getting better is because we learn more and more how to prepare this solid deuterium. This is a huge block of a solid that you have to freeze, and the better the quality, the crystal quality of this thing is, the better is your UCN output. We have two things we do. We do one thing, and that's shown here. This is just UCN counts on a detector that you would mount at the end of a beamline, and all the valves here and here would be open, and we take a 2-second long pulse. And we do that every year in order to be comparable. So you see the pulse will stop after 2 seconds. This is here, 2 seconds. Then the neutrons need some time to get to your detector, another 2, 3, 4 seconds, whatever, until they reach the detector because they're so slow. And then it's fast dropping here. And that has to do with, for that measurement, this flap is open. So they just fall back down into the moderator. Obviously, you wouldn't do that if you really want to produce many of them. And you see the difference here. This is now logarithmic, but the red one is what you see here. And if you close these big valves, then you can, over many minutes, drain ultracold neutrons from the storage container and do your experiments with them, whatever you like to do. Now, I was telling you, everybody says they have the best UCN source, so I do the same. Now, the way how I do that is I tell you, in order to do something that we could compare different UCN sources, we built a storage bottle, a typical storage bottle, we call it. It's just a stainless steel tube, about 30 liters of volume. That's representative for a neutron electric dipole moment experiment volume. And then we bring that to all the sources we had, and Dieter Ries did that in his PhD thesis. He traveled all the UCN sources with this bottle and would try to adapt the bottle best to the given UCN source. For instance, at PSI, you go up a little bit with the bottle because then you can store some more UCNs in that. For others, it will be on the same height. It will perhaps be even higher. You can do different things. And then you measure how many UCNs you have in your bottle after, say, 50 seconds of storage, that would be here, or after 100 seconds of storage here. And you measure at the same time the storage time constant in your bottle. How long would your neutrons survive in this bottle if you look at an exponential decay? You have other losses. It's not the beta decay, but they disappear from your bottle through other processes. And then you see these storage times are not only a feature of the bottle, but also of the UCN source. And that has to do with the fact that, for instance, here, this is at ILL, the source I was showing you in the beginning. This has a very hard spectrum. So the neutrons are pretty fast. They will have many wall collisions, and they can be lost on every wall collision. So they don't survive as long as in our source or in our storage bottle adapted to our source, because then the spectrum is slower. But if you go, for instance, to ILL, to Oliver Zimmer's superfluid helium source, they are even slower. So neutrons survive much longer there because they will collide much less with the walls again. So you see, depending on what you want to do, you will have different quality of sources for that experiment. To be fair, the trigger I should mention here as an installation in Mainz would be much better to fill a small volume. If we take a 30-liter volume, that's not ideal for this source. But if you fill something that's only 1 liter or 5 liters, then maybe you get much higher densities also at trigger. Now, I'm at the end of my chapter 1. The thing I wanted to tell you is ultracold neutrons are those that we can trap in this volume, for instance. Think of that being a cylindrical evacuated container, a top lid and a bottom lid. If you do a very, very good job, then you can store them for many minutes. And in principle, you're only limited by the neutron beta decay lifetime. They behave like a cold gas, a really cold gas, so they are affected by gravity. You can very efficiently count them, almost 100% efficiency. I didn't talk about counting at all. And they can be 100% polarized. And that's the things that you need to know in order to now understand what you can do with those. And this would be my chapter 2. Klaus, are there questions I should answer, or shall we continue at that point?
I don't see any question, neither in the chat room nor in the question and answer room. So I propose that you continue. And
okay, so let me just continue. And now we get into electric dipole moments. And what I show you here is from 1928, a paper by Paul Dirac. And I show that because he was developing his quantum theory for the electron, where you see a magnetic moment interaction with a magnetic field H here. And he also writes an electric dipole moment interaction with an electric field here. And what you realize here is this I. So this is a purely imaginary part. And he also discusses that, and he said it's doubtful whether the electric moment has any physical meaning, right? Because it's this imaginary part here, and the Hamiltonian obviously should be real. He realized obviously also already that this would be violating some symmetries, and people have pointed that out later. Li and Yang did, Landau did, others did. On the experimental side, mainly Purcell and Ramsey did. And they pointed out that although we all assumed in 1950 that parity would be a good symmetry for all the interactions, we didn't know. And they suggested one could test that with electric dipole moments. And obviously we're thinking of the neutron at the time. And here depicted is a neutron, or another particle, could be an electron as well, would have a magnetic moment, would have an electric dipole moment, and would be exposed to external electric and magnetic fields. And then you can exercise this game just looking at D and E. Forget about mu B. We know there's a mu dot B interaction. Let's look at DE. If you do a time reversal, then the electric field doesn't care, right? I mean, if you think of the electric field from a plate capacitor, the charges will always remain, whether time goes forward or backward. The electric field direction remains. But then the angular momentum of D, which is coupled to the spin, there is no other direction in the system than the spin will change direction. So now D dot E changed sign from here to here. So if it's not zero, it's giving a contribution to the energy. And this is time reversal violating. The same argument will be made for P if you want. Now let's look at T. and then we say all our sound quantum field theories today, they have CPT conservation, right? That's a theorem, a very strong one, and based on very general assumptions that perhaps we don't want to sacrifice. We could, but we don't want to do that for this argument here. So T violation must be coming together with CP violation in order to fix CPT. Okay, so that's a probe of CP. And this is the reason we want to do that, because we know from looking into our universe that we have no primordial antimatter left from supposedly a symmetric Big Bang, which produced matter and antimatter. So antimatter disappeared. And then in 1967, in a paper, Sakharov sort of gave the 3 criteria that he said a theory must fulfill in order to be able to explain the baryon asymmetry that we observe. And one of those is CP violation that we need. This is just the observation of the baryon density in the universe minus the antibaryon density, which is essentially primordially 0, right? We don't see any normalized to the number of photons, so the cosmic microwave background photons. This is order 10 to the minus 9, okay? And then what you would expect from the CP violation of the standard model, just in the CKM matrix, put into standard cosmology would give you something that's 9 orders of magnitude smaller. Okay, so that's a huge discrepancy. We don't understand that. We think we know we need additional CP violation beyond the one known in the standard model. And this is why you look for EDMs, because they are super sensitive to that. And because Dima was using elephants last time, I thought I'd bring my elephant here, which is to show you the complementarity of what many of us are doing. I mean, we are more on this side here, the high intensity, high precision frontier. This is a diagram of a quark EDM where you have a quark CP violating coupling to a photon. And this would be mediated in this case by some supersymmetric particles over here, which would leave the traces of the things in the loop that you don't know. You see an EDM, you don't know what it made, it just left traces. And that's complementary what you could have at high energy physics colliders, where you would produce elephants and whatever beasts perhaps directly. Now, EDMs in the standard model are tiny, tiny. For quarks, this will somehow come to 3 loop order. Neutron proton has been estimated 40 years back by Kriplovich and company. Actually, the same Sitnitsky as Dima was referring to last time. 10 to minus 32 would be the order of magnitude here. I put here 10 to minus 30 because if you squeeze your theory friends, they will say, well, look, I mean, the 10 to minus 32 perhaps could be 10 to minus 31. And then you say, well, what about a little bit? And then they say, okay, if it's 10 to minus 30, it's probably non-standard, at least not from the CKM phase. Experimentally, we are some 4 orders of magnitude away from that. It's even much more for leptons. If you look at a bare electron EDM, 10 to minus 44 in the standard model, comes only 4th order electroweak, and the experiment is 15 orders of magnitude away from that. But there has been amazing progress in the past on that. The little grain of salt I just want to put in here is that comes from, not from bare systems, but the electrons are constituents of molecules, so there could be other interactions as well. But then you say, I don't care if I have 2 miracles, it's even better than just 1, right? I mean, so you look for an EDM, and if the effect you see comes from something different, you'll also find out what it is eventually. Okay, now we look more at the neutron here. Taking the neutron as an example, I could do the same with the electron. There are 2 named problems, CP problems. This is the SUSY CP problem. What I show here as a function of the year are just the published limits of the neutron EDMs. It starts with Ramsey, Purcell, Smith. They published in 1957, the 1950 measurement, right? After the discovery in 1956 of parity, they thought, oh, now it's worth publishing also the neutron EDM. And then it went off here. Now, the SUSY CP problem is the following. In the most naive model, where you have just 1 CP violating phase in the SUSY, and you say this should be of order 1, and you would have masses so small that, say, you could still survive with the LHC bounds of 300 GeV or up to 1 TeV or so, the dN would be 10 to minus 23 or 24 electron centimeters, would be excluded by now. So the phase must be small. Then why should the phase be small? Is there any reason? We don't know. If the phase would be large, then you could make the masses large as well, right, to suppress the Dn. So ask, why is the mass 10 TeV or 100 TeV or so? And we don't know. If you go away from the super naive model to, say, allowing for 2 CP validating phases, you get a little bit more complex model. And then you see what you need. For instance, here the constraints come from the thorium oxide, which is an electron EDM limit, and then a nuclear EDM limit from mercury 199. And they will constrain both phases at the same time. Right? The neutron doesn't look so good in here, but there are other models where the neutron looks better. Just making the point, if now you say, oh, 2 phases is not enough, let's take 4, a model with 4 easily built, then probably you better have 4, 5, or 6 different systems where you look for EDMs to constrain that. And the second named problem is the so-called strong CP problem. This is the fact that in the QCD Lagrangian, there's this GG dual term here, which is CP validating. The theta parameter in that can be related to the neutron EDM by this numerical factor. It's an estimate only, but this means by the experimental limit on Dn, this theta has to be very small, 10 to minus 9, better 10 to minus 10 or smaller. So why is that so small? Theta is the only parameter in the standard model that could still be exactly 0, right? It's the only one that's so small if it's not 0. We have no idea whether, or we have many ideas why it could be, but we don't know what's right. One of the ideas was also discussed by Dima last time. I mean, you introduce axions to make this strong CP problem go away, but then you have to find another particle that does the job, okay? So if it was like that, if we would have order 1 CP violation, the strong interaction, Ramsey and Purcell would have seen it. Now, how do you measure the neutron EDM? Well, take my box I was showing you before, put polarized neutrons into that, do a pi-half flip, and measure the Larmor precession in magnetic and electric fields. Here's the precision, so you have the mu.b and the d.e term. Well, then you reverse one of the fields, say the electric one, you get a minus e here. You have these 2 frequencies measured, measure the difference of those, and then the B drops out, and you are left with the unknown D and the known E, right? So you divide that over here and get an expression for D. So that's super simple in a way. If you don't like this precession picture, you just look at the energy splitting in the fields, and you see that you have to measure this energies here. The sensitivity on the Dn observable in your experiment will, everything's proportional to h bar, right? Will be proportional to h bar. Then it has an alpha here. I show you that in a moment. This is essentially the analyzing power for the polarization of your neutrons. Then you are linearly in the electric field and in the free precession time t, while you sort of let your system evolve here. We see that in a moment again. And then we always need to count ultracold neutrons, so it will be a square root n term in here as well. Now I said it's easy. It's not, and you see that if you put in some numbers, the mu.b interaction is such that at 1 microtesla field, this is the field strength that we use, we have a 30 Hertz precession of the neutron spins. If you take our electric field, which is about 11 kilovolts per centimeter over 12 centimeter here in our chamber, and you say, well, let's just go below the present best limit of the neutron EDM, 10 to the minus 26 electron centimeters, it will do just 1 turn of the spin in 200 days. So you need 10 to minus 9 or better precision on that one, meaning on the field essentially. 10 to minus 9 on the microtesla brings you to femtotesla, and that's impossible, right? We cannot control our field to 1 femtotesla. So now you start to play tricks to sort of release that somewhat, to bring that to a few hundred femtotesla or so that you could survive with your measurement. This is a picture of the experiment that does the job. Here is this chamber I was just pictorially showing you. This is 0.5 meter diameter, has a top electrode at high voltage, has a ground electrode, which closed this bottle. There's an entrance shutter. Neutrons can come from below to fill this. Then it's sitting in a vacuum tank. The vacuum tank can be closed with this lid here. If we put the lid on, you see the wires on that we produce a vertical magnetic field. And obviously this is a large plate capacitor. We have a vertical electric field as well. And then it's sitting in a 4-layer mu metal shield. Overall diameter of the outermost shell is some 2 meters here. Here you see the beast installed in 2009 in a thermal insulation at PSI. That's super important in order to keep the mu metal happy and keep the fields from drifting. And over here you see a sketch where the superconducting polarizer magnet is shown. So UCN come from here through the superconducting polarizer into the system from below into the chamber, which you see again here, through the superconducting polarizer from below into this chamber. Then when we have enough in here polarized, we close the door, we empty all the rest out into a detector down here. We count the neutrons as a reference. We put the switch in a position that later the UCNs from here will fall into the detector when we want to count them. And then we have polarized neutrons in here. We can flip their spin. We can have them freely precessing, and we can later analyze how many are spin up and are spin down. And during we do that with the neutrons, we fill the same chamber also with polarized mercury 199. This is also a spin 1/2 nucleus in this atom. It's a diamagnetic atom, so it has a very long spin coherence time as well. We can optically read that in situ, and that's a huge advantage. So we'll flip also by 90° the mercury spins, and they will be spin precessing here. And then we have a mercury light, circularly polarized, that goes through, and the spin precessing mercury will modulate the amplitude of this light. And so we do an online readout of the Lama precession. And from the mercury 199 EDM experiment, we know that the EDM of the mercury 199 is negligible for our purpose. So we use that as a reference magnetometer here also in the electric field. Then we have cesium magnetometers on the high voltage electrode and below the ground electrode. So at many points in space, we can also measure a magnetic field magnitude. And from those, it's 15 measurements we have in total there, we can reconstruct magnetic field gradients. While the mercury and the neutrons are measuring one averaged value for this chamber, and they differently average that a little bit, but the cesium magnetometers can measure magnetic field gradients that cannot be corrected by the mercury itself. So when you have the mercury and the neutrons together, you can, for instance, measure the ratio of magnetic moments of the two. And we did that already in a preparation measurement in 2012. And then you start to appreciate how well people measured, for instance, the neutron magnetic moment in 79. I think that was Jeff Screen's PhD thesis or so. And then even older is a measurement of the mercury 199 gyromagnetic ratio. Both of these need to be improved. This one will be improved offline. This one here will be eventually improved when we improve our limit and combine it with a new mercury measurement. Just to tell you, you can do a ppm measurement or sub-ppm measurement of the neutron magnetic moment, although you never get as good as for the proton or the antiproton with that. What we then do is we apply Ramsey's method of separated oscillating fields. So here's the spin up neutron. We apply a pi-half spin flip. We have a free precession period. We apply a second pi-half flip. That's a clock comparison between this neutron in the magnetic field and its Lama precession and an external oscillator that you see over here. At the time when we want to have the pi-half flip, we gate in this oscillator frequency as a transverse field or rotating field to flip the spins, and then phase coherently after some time, we come with a second pi-half flip. If they are perfectly in phase, we will be on resonance, and everything that was spin up will be spin down in the end. This you see over here. This is an asymmetry, n up minus n down spins over the sum. So all spin down is here. Well, you see 75%, not all, but this is sort of the polarization we would typically work at, right? We have a little bit of polarization loss in the experiment. You see, we do that for 180 seconds free precession. So 3 minutes of free precession, and the polarization lifetime, the T2 time of our neutrons can be well above 1000 seconds in this case. And then you see you would get this Ramsey fringes here. If you're not familiar with that, the thing you are familiar with is a double slit experiment with light. This is a double slit experiment in time, right? They are the 2 pi-half pulses, the slits in time. The mathematical solution is exactly the same interference pattern. Now we go to the central fringe, we go to the steepest slope of the fringe, and we will measure at 4 points this curve and then interpolate and find the frequency of the minimum here, okay? So this is now with some real data. The central fringe, you see we measure only at 4 points. Look at the solid line first. The positive and negative electric fields are just on top of each other, fine. This we didn't do in the analysis. What people got to analyze was data where we artificially blinded the data by introducing a finite EDM signal that was randomly picked, but a small one, but a finite one. And you see here, there's a fit with a negative electric field on blinded data. And you see this Ramsey fringe is shifted a little bit to the left. And then the other one with positive electric field is shifted a little bit to the right. And this is exactly the signal that you have from an electric dipole moment. And now you have to find out that, and we blinded the data in order to get any bias of that people could have to find either a finite value or confirm zero, whatever. We had 2 independent analysis teams. They would get different blinding offsets. When everybody was happy, we did some rough comparison to make sure we could then take off the relative blinding, and then they would coincide, and they did. And then after some more systematic check, we unblinded the full result. This is just a sequence of raw data. You see the neutron frequency in the upper graph as a function of cycle number. So every cycle takes about 5 minutes in our case, 300 seconds of which, 3 minutes of which are free precession. And the blue is 1 electric field direction, the black is 0 field, and then the opposite electric field, and so on. And you see the magnetic field is drifting, and it's drifting quite a bit, and sometimes it jumps. And this is something we tried to shield away, we tried to stabilize, it doesn't work out that it's gone completely. But what we then do is we calculate this R ratio, which is the frequency of neutron to mercury, and then you get a super flat line over here, okay? Now I could tell you a lot about systematics. I'm going to skip that in the moment for the sake of time, and just tell you that it required a lot of in situ magnetic field measurement, but also field mapping of the apparatus in order to retrieve a higher gradient magnetic fields that we needed to subtract. And also we did offline scanning in Berlin at the BMSR2 facility, where there's a large squid magnetometer and a large magnetically shielded room where we were confirming that we have no dipole contaminations on our equipment. In the end, you calculate the neutron electric dipole moment as a function of this ratio of neutron to mercury frequency, and we introduce on purpose small gradients in our fields. And then the neutron distribution sits slightly below the mercury distribution. This is because the neutrons are affected by gravity. They sink in the gravitational field, whereas the mercury is really a thermal gas. So a gradient will shift the ratio of frequencies here because they average differently the magnetic field. And then we get for one field direction and the other field direction a linear slope here that we can look for the crossing point and find the true R value. Well, that's not the full story. There are also some corrections to that. I'm not going to bother you with that in the moment. If you want to ask questions, I'm obviously happy to answer. Now, this is the table you may have seen in our publication. This is now in 10 to the minus 28 electron centimeter steps, our error budget, the systematic errors that we have, and the way how we fight them. You see that the biggest ones still come from magnetic fields. This one here is something that we need to fight with offline measurements, the high order gradients with mapping, then this with measuring here over here, the equipment at PTB, and then this is in situ measured. We can talk about the scattering length of mercury if you wish. This is also an interesting one that came to us only in the analysis. Now, and this is the final result of that. It was a super surprise, and I would have guessed you cannot get that just by accident, but here it is. It turned out that the central value of the two analyses was exactly 0. This is the statistical precision, and you see this is only something like 40% or so improvement over the past one. So that was measuring for 4 years or so, and we have some 2 years of data. But the major improvement, almost a factor 6, maybe here 5 rounded, is in systematics. And that gives us a lot of confidence that we can do in our next step even an order of magnitude better. So here's the new limit. We are working on this N2 EDM successor, which, well, hopefully doesn't take 10 years, but we've put it somewhere here to say we're not so sure when it comes. It's being assembled in the moment. We'll take the first UCN into it next year, hopefully, and then we'll need 2 or 3 years to debug and to find out what needs to be done better. This is a sketch of it. This is the platform for it. There was a new foundation built. Here is a magnetically shielded room that has just been finished last year. So this is 3 of us standing in front of that. This replaces the thing that had 2 meters diameter before, right? That's a 5-meter cube size thing, now 6 layers of mu metal to get a larger shielding factor, but also to get the innermost mu metal layer further away from the sensitive experiment, and in order to allow for a much larger volume that we can fill with neutrons in order to improve the statistics. And with that, I'm through that. And Klaus, let me ask you whether we want to take some questions or whether I should stop at all, or whether you want to have 5 more minutes or so of these exotica.
At the moment, Klaus, there is only one question. I propose to postpone it until the end of your talk. If it takes another 5 minutes or so, that should be fine.
Yeah, I will do very quickly, and just as an appetizer for you, that if you think you do such an experiment for 10 years and you would be measuring only one number, that may be a little bit frustrating, right? So you start thinking what you could do else. I was showing you already a measurement of the magnetic moment that you can do. Here is some more things that have to do with dark matter, and Dima was talking already about ultralight dark matter. They can also be heavier, obviously. I mean, we don't know where the mass of dark matter particles is, which justifies that we look at all kinds of possible mass particles. This is now looking for a mediator for an exotic interaction that could be axion-like. So it's a scale-up, pseudo-scalar coupling between a porized neutron and unporized nuclei in the storage chamber. And we look at masses of a fraction of an electron volt to millielectron volts. And then what we measure is a spin-dependent exotic interaction. We don't find that. We place a limit in such a plot where the interaction range is a parameter of a Yukawa potential. I leave it like that. And if you're interested, you just look into that, only to tell you we update that soon and hopefully get somewhere down into this range to test for smaller couplings, right? It's all about getting to small coupling strength in this business. Another thing is, let me just jump to the result here, is a measurement where we search for oscillating EDMs. I told you everything about the permanent EDM search. Now we can look for a oscillating EDM, which could be induced by an ultralight field, axion-like field. And Dima was talking a lot about these. We searched for that in all frequencies. You see that from inverse minutes here to inverse years. We didn't find any, so we put a limit on the oscillation amplitude, and then you take some model if you want that has an axion coupling to gluons. You introduce the axion mass or their frequency, and you get an exclusion plot in this plane, right? And again, I just invite you to look at this. This was the first laboratory limit in that plane at all, besides astrophysical and cosmological arguments. And Dima was already last time mentioning a caveat in these arguments where if you have this very slowly varying field, it could be that you are just at a position where you don't see any effect, right? And then the limit doesn't mean so much, and you have to sort of account for that. The way we do that for the time being is we tell you when we measured, and as you find in 100 years that it changed, then maybe we know the reason why. And I think I'm through. So there are many more side analysis that you could do. I skipped over this one, which is a search for mirror dark matter, where the dark matter in this case would be GeV particles like the neutron itself, and you would find disappearance of your neutrons from your experiment. But again, you can look it up if you're interested or ask me questions about it. And then I'm done. Otherwise, it's get too long.